It's a procedure that we learned for coming up with a confidence interval. And what we're going to do in chapter 15, they're both called Z procedures because one of the conditions out of the three conditions is that we do not know mu, but we know sigma. So because of knowing sigma, they're called Z procedures, like the Z scores. So, remember we've got three conditions, and I just named one of them. So, the third one is not knowing mu, but knowing sigma. What was the first one we've listed? Okay, then we have information from a sample that is a simple random sample, and that there were no problems like non-response or anything else like that. Okay, somebody else, what's the second one? We have the individual scores in the population normally distributed. Yep. So between that and knowing sigma, that's what makes how we came up with the confidence interval, and what I'm showing you in chapter 15, Z procedures. So the data that I re-entered into the calculator before we started class, we had looked at that on Wednesday, and it was about if you were to take some newts, amphibious newts, and anesthetize them first so that they don't feel the pain, give them a cut along their back or something like that, and then look at the rate that it's healing at. So these numbers were in micrometers per hour. And we had 18 of those newts. So 18, what number, what label could we give to that number 18? The 18 newts, little n. Okay. So again, this came from a previous edition of the book. You may or may not find it somewhere, either in the reading or in the exercises of this new edition. But in the old edition, they told us that sigma, the population standard deviation, was 8 micrometers per hour. And they were coming up with a 95% confidence interval, or CI for short. We haven't covered that part yet. So, one thing is missing here. What has not been stated? Of those three conditions, what has not been stated? Oh, sorry. Assume that's true. And we've got sigma. So then what do we? Okay. Well, what we did at the end of class was to make a stem plot. We split stems. And I was suggesting, this was right at the very end of class, that it probably was skewed right. And a single peak, and then we had more going on this way. Well, if I didn't show you this before, you can enter in the data and press that, and then edit. Sorry, edit was for putting it in. That we already did back in chapter 4 and 5. So go to calc. So go to calc and just pick the very first option, which is short for one variable statistics. I put it in list 1, so we'll get it from list 1. What might be some important information that we need from that calculation? It's come up with all sorts of things. What might we need? X bar. Because we have our formula, X bar plus or minus Z star times what? Sigma over square root of n. Okay? So I'm going to copy down that we've got X bar is 25 points, and I'm not going to round it. It's probably 7 5s there, followed by the 6. But the other thing, remember different presentations of a stem plot or a histogram could give us different ideas as to whether something is symmetric or skewed left or skewed right. So what can we compare X bar against? Yeah, and if we scroll down, there's the median, 26. So, although we do not need that for our calculation of the confidence interval, we can make our comparison, and they're close, so maybe it's roughly symmetric, but if we had to choose skewed, which direction does this tell us it's skewed? When the mean is less than the median. Skewed left or skewed right? Actually, this is telling us that lower scores are pulling it down. It's pulling the mean down, skewing it left. So I couldn't quite tell that from my picture the other day. There was that lump of 3 that was at the top there for the lower stems. It was a little hard to tell if we had high scores dragging it up, or if that lump of 3 at the other end was instead dragging it down. Thing is, we haven't covered anything else for what to do if it's not a normal distribution. And they're really, really close. Maybe it's just because it's a sample. And there were only 18 of these nukes. Maybe if we had 1,000 or 250 million or whatever, then maybe we see in the stem plot something that looks more and more like a normal distribution. So we're going to acknowledge the fact that maybe it's not normal. From what we see from the sample, it's skewed left. We're going to assume that it is normal, though, and proceed. Okay? We'll proceed with caution. I neglected to open up table C, but got the book handy. Turn to table C and find the Z star that goes with 95%. It's going to be towards the bottom. Find the 95%, follow it down to the Z star row that's towards the bottom. 1.960, which is 1.96. All right. Then if we take without rounding, this mean what was sigma? 8. And little n was, okay, so we're going to divide by the square root of 18. If you don't like having to copy down such a long decimal, I think there is one more thing. Let me look. Yes. If you press second and above stat is list, go over to the map. And the third option is mean. You would have to tell it the mean of list 1 And therefore, the calculator will put in for that the 25.555555556 for you. Do the subtraction to get the lower bound. So 1.96 times 8 divided by square root of 18. And let's go ahead and round to the nearest tenth on this one. This is giving us approximately 21.9 for our lower bound. Remember, don't round unless the directions tell you to, and go to the place that it says. For the upper bound, let me change the mode on this so that you can see the whole line I put in there. So the previous thing I did, if you want to read the whole line, looks like that. And if you've got one of these newer ones, again, you can do a little copy and paste and just switch that minus to a plus. If not, well, hold it like you hold your phone when you're texting and use multiple fingers there to type it in quickly. What's that to the nearest 10? 29.3. Okay, that's our upper bound. Written in integral notation instead, if you're comfortable with that. Remember, left to right, least to greatest. So 21.9, comma 29.3, and then we've got parentheses around it. On the quiz, you're going to have to do an interpretation. So here it is once again. Since this was a 95% confidence level that we used, if we were to go take all the newts in the world and all possible samples of size 18, so that at some point each newt would be in a sample at least once, probably many times, but get all of them of size 18, do the same confidence level of 95%, get a confidence interval for all of those. Same size sample, same confidence level. Then 95% of those confidence intervals we would come up with would actually have the true population mean in there. The short version of that, not the one I'm looking for on the quiz, but the short version of it is, that one has a 95% chance then of having mu in there. Questions? Okay. So let's use this same example to begin chapter 15. We're going to get about 20 minutes worth of it in here today before the quiz. You have the same set of conditions to be able to use the procedure I'm going to show you today. It's called hypothesis testing. That's one name for it. Based on the numbers I'm seeing, I'm going to pick a number kind of out of the air, but not totally. What if I made the claim to you that if we considered all newts, the average rate at which one of their wounds would heal would be 24 micrometers per hour. That 24 happens to be in between those two things. I'm sort of grabbing it out of the air, but I'm basing it on what I'm seeing there. So say we want to test that, particularly if we've not even done this work. If we want to test that claim, we're making a claim about the population mean, just like the confidence interval, we were looking for something that had a high probability of capturing the population mean, mu. So test the claim that mu equals 24 micrometers per hour. I don't even know what the abbreviation for micrometer is, so I'll just write it all out. Micrometers per hour. Then that's the first thing we have to do in this procedure of hypothesis testing. State what your claim is and state an alternate claim. Let's say that all the evidence up until this point has suggested that's really what it is for the whole population, or that for some reason it's a long-held belief. They call that claim of a long-held belief, or what all the evidence has pointed to so far, the null hypothesis. And it gets abbreviated as H with a little 0 written below it as a subscript. And it gets read as H naught. This is a colon, and we would write mu equals 24. Let's say somebody else comes across some other recent evidence that suggests otherwise, and so now they want to actually go through the rigmarole of testing it. They would have an alternate or alternative hypothesis. And there's different ways it can be set up. We abbreviate it as HA, and I'm just going to show you one possibility today. Simply that it is not equal to what was previously claimed. So mu not equal to 24. They call that when it's not equal, when you're saying the alternate is it's not equal, they call that a two-sided test. The reason for that is, if it were a one-sided test, I would be making a claim about either it's less than 24 or that it's greater than 24. I'd be picking one side of 24 where I think mu really is. Here I'm just saying it's not equal. It could be either more or it could be less. It could be on either side, hence the two-sided test. That's going to affect at the very end when we talk about the probability of getting the sample we did, how we make our decision. This is like a court case. What do we assume in the United States when something goes to trial? Or at least, what are we supposed to be assuming? Innocent until proven guilty. So in this case, assume this until you've got good enough evidence in support of the alternate instead. What counts as good evidence? I gave you a hint before break. Remember that basketball free throw example from the author saying that he claimed he could make 80% of his free throws successfully? And then we came up with a low probability. If his claim was true, and then we ran this experiment and he only made something like 4 out of the 20 successful, well, was that just a really bad day, or is his claim not true? We came up with such a low probability, it would have to be a really, 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 really bad day. So at that point, we said it's more likely that he was lying. He's not that good. Okay? Step 2, I think I have on here. This would be on the second page. Yep. Well, then just how long are we going to let it be before we're convinced? The number I'm going to pick here is not out of the air. What confidence level do we have for this? I've erased it, but what confidence level were we using? 95%. If I said I was going to set a significance level for this test of 5%, where do you think I'm coming up with that? What's the relation between 95% and 5%? Okay? They'd be probabilities of complementary events. Exactly. Okay? The symbol used is the Greek alpha, which is a predecessor of our letter A. If you draw it carefully, it will not look like sigma. It's only when you draw sigma or alpha kind of sloppy that you will get it kind of looking alike. So I'm setting a significance level of alpha equals 5%, or we may need to write it as a decimal, 0.05. So this is very important. If I were to get the sample that we were using earlier, which had its sample mean was that 25.5 repeating, how close is that to 24? Well, we can't really tell just by comparing the two numbers, because there are things like, well, what's the spread of this normal distribution? We're going to calculate a z-score here to help us do this test. But when we find the probability of that z-score occurring, if it's bigger than 5%, we're going to say, not good enough evidence to go in this direction. Let's stick with the null hypothesis. The null hypothesis is innocent. So only if we were to get 5% or less, then we would say that we've got a lot of evidence against the null hypothesis. It's almost like saying guilty. Be careful with the language. I wouldn't say I accept the null hypothesis. I'm sorry, did I accept the alternative hypothesis? I would say I have a lot of evidence against the null hypothesis. Okay, so, because of what we learned in chapter 11, with the sampling distribution of x bar, we've got x bar minus mu. Actually, the mu that's in the null hypothesis. So sometimes we're going to write mu naught there over sigma divided by 1. Square root of n again. Okay? So we had that 25.555.555.6. Subtract from that the claimed mu in the null hypothesis. What did we have for sigma? 8. When we did the confidence interval? Sigma was 8. Okay. And little n was 18. So over square root of 18. Just to confirm that bit about going to the list above stats, and then the math submenu, if I tell it to take the mean of list 1, there's that same number that we found from the one variable statistics. Take away the 24. So your numerator is going to have 1.5555556. When we divide that numerator, what have you had to do on the calculator to make sure you're getting the same answers that I get and that the authors get in the book? When you put in sigma and n, put parentheses around that fraction we're divided by, that's one way to handle it. So 8 divided by square root of 18. you go to table A, be careful. It can be done. Instead, we're going to look at something on table C. Still, well, it's going to be nearby the Z star row. Let me draw a picture before we interpret this. We're going to, when using table C, round that to not 2 places, but 3. Because that's how exact table C will get. This is approximately equal to 0.825. So here's the deal. Since we're doing a 2-sided test, and I'm telling you that what that would mean is between that and our significance level, we would only be convinced that the probability we get is at or below 5%. Since it's 2-sided, what we would have to be talking about is a very big z-score, a very extreme z-score, so that the probability of being in one of those 2 tails, 2-sided, 2 tails, a total of 5%, which means there's 2.5% per side, we'd have to have such an extreme z-score, we're out in one of those 2 tails, that the total probability would be 5%, half per tail. We made the claim that U is 24. Where is that X bar in relation to the 24? The z-score is telling us that. But is it here in a safe zone? Since it's bigger, I'll put it on the right-hand side. Is it in a safe zone? In which case we would say we get a low probability, and so we would not reject the null hypothesis. It's like saying you're innocent. You failed to convict. Failed to reject the null hypothesis. Or is X bar so large compared to the 24 that it's one of those extreme scores that's unlikely to happen if that claim was really true? Is it so unlikely that we would say the claim's probably not true? Reject the null hypothesis. So you would convict it. Fail to convict or convict the null hypothesis. Fail to reject or reject the null hypothesis. By the way, you could use normal CDF to, without even getting the z-score, put in 24 and, no, sorry, you would put in the X bar and then 10 to the 99. I know to go upwards because X bar was bigger than the claim U. Then you would put the claim mu of 24. And then you would put the sigma over square root of n, which was the 8 over square root of 18. You have to do one more thing though. Double it because it's a 2-sided test. That would give you the probability directly. If you're going to use table C instead, this is on page probably 679 or something like that. Yep. Underneath your Z star row, there's 2 more rows. One-sided P, which is a probability for a one-sided test, or 2-sided P, a probability for a 2-sided test. So, in the Z star row, Find the two closest values to 0.825. The two that would be closest to 0.825. That's why I went to 3 places, because the Z stars are the 3 places. I'm going to give you one of them. Below it is 0.674. Above it, the very next Z star value shown is what? 0.841, and that is above this one, right? Okay. So all you have to do here, rather than an approach that we could use table A for, like I say, it could be done, but the problem is, when we don't know sigma, things get more complex, and we can't make multiple tables for it. We're going to have to use table C. Table A, being about z-scores, assumes you know sigma. We're going to drop that assumption in chapter 17. So it'd be better if you learn this method, and if you want to double check it with normal CDF or something from table A, okay. But later on, we absolutely have to know how to read table C. So real quick here, above that below it, in the two-sided P row, what's the value in the two-sided P row that's below 0.674? 0.5? Okay. And what's below 0.841? 0.4? Which one's bigger? 0.5 or 0.4? 0.5. So notice the direction change. Remember, the further out you go, bigger z-scores, smaller probabilities. So for full credit, when you're using this approach rather than normal CDF, write it with these reversed compared to these. This capital P is saying, what's the probability that we would get the sample we did with a mean for the sample of 25.555, 555, if in fact the mean of the population truly was 24. Well, what are these as percents? 50% and 40%. What is 5% in relation to these things? Alpha was 5%. Where is it in relation to the 50 or the 40? It's even less than the 40%, right? Okay? And that's what matters. If P is bigger than alpha, you fail to reject. It's like failing to convict in a court. Fail to reject H0. That's what we're doing here. All right, off to the side. If it had been that P was less than or equal to alpha, then we would reject. So what our interpretation here is that from the evidence we have from this sample, we do not have enough evidence to go the other direction. We do not have enough evidence specifically to claim that the mean healing rate is different from 24 micrometers per hour. Make sense? We're going to get plenty of more experience with this, but I wanted to get one full example in before starting the quiz. So next week we'll see one-sided tests, problems that we may wish to avoid, what happens when you change N or alpha, similar to what we did with the confidence intervals on Wednesday, and so on. So there's going to be plenty more practice coming in with this stuff.